Welcome everybody to today's Research Pays Off. My name is Lauren Dow. I'm the Communications Coordinator for the National Road Research Alliance, and I'm recovering from a bit of a cold this weekend, so I apologize for the sound of my voice today. Today we are launching into our series of the product team updates as a replacement for this year's pavement workshop. And so we are starting off with the Rigid team and their presentation about the performance benefits of fiber reinforced thin concrete pavement and overlays. And we have both Manik Barman from the University of Minnesota Duluth and Tom Burnham from Minnesota Department of Transportation with us today. So I will turn it over to Manik and we will get started.
Thank you, Lauren. So we recently completed this research and then Lauren introduced the topic. Yeah, we really appreciate the funding from the NRRA. This project taught us a lot of things which we will be looking at in this presentation. I really would like to thank Tom Burnham especially for helping me or the research teams with this project. He was the technical liaison, but I would just say like he was part of the research team. He helped us with the research work tremendously. So along with me, we have graduate students, researcher, and also in the last couple of months of this project, we had a postdoctoral associate helped in some data analysis and report revision. The special thanks to the TAP members, colleagues from different states participated and shown interest, made good and fruitful comments on different tasks that we wrote for this project. And then I would like to thank all my MinDOT colleagues who actually helped us by collecting data and providing data to us. Without those, we could not have finished this project. So I really sincerely thanks to them, especially Len, Joseph, Ben, Dave, and many other colleagues whom I probably personally do not know. So thanks goes to them. Okay, so what are the research objectives? So we know like fiber reinforced concrete is not new, and then in pavement it is not new too. So in different states or in different research project, mainly laboratory based fiber reinforced concrete have been using. We know like there are a lot of different laboratory tests which can characterize the fibers influence on the concrete material behavior, but there are really not a lot of field projects where the performance of the pavements were studied or how the fiber influenced the performance. This unique project actually gave that opportunity to study the influence of synthetic structural fibers when they're used in ultra thin or thin pavements and concrete overlays, how they influence, let's say, fatigue cracking, transverse joint faulting, or can we change the or can fiber benefit provide some help in slab size increase. Also, this project we targeted to get to know like what kind of structural responses are influenced by the fibers. If we also saw like joint performance, like load transfer, how fiber influences them. And lastly, we also saw like the ride quality, which is really important and influence the user. So how fiber can influence the ride quality. So all those things we have investigated. So today what I'm going to focus on some key questions or what we learned basically from these research projects. So the questions we had, can structural fibers help to construct ultra thin like 3-inch or 4-inch thin concrete pavements for low volume roads, city roads, those? Can macrofibers mitigate fatigue cracks and transfer joint faulting in thin concrete pavements? If so, then what is the relation with fiber dose and residual strength? Can we construct thin concrete overlays with wider slabs when we use microfibers? And what are the influence of fibers to the pavement responses? So those are the key questions that we had, and then I will be focusing mainly on these 4 questions. Let's see what type of answers we get. Now, in order to know the answers for those questions, in 2017, 8 cells were constructed. Excuse me, did anybody tell anything? Okay, so there were like 8 cells. 2 were constructed on the low volume road test track 139 and 239, and others were on the westbound I-94 section of the main road. And all those cells were designed basically for low volume roads. Okay, even though 6 of the cells were constructed on the I-94, we actually applied accelerated load like under interstate traffic. So those are not designed for 20 or 30-year interstate traffic. These are intended for low volume road. So that we can see the failure early, those were constructed on the interstate. So out of the 6 cells, the 4 were actually constructed on concrete, on gravel. Okay, and the other 2 were actually concrete overlay. Okay, so now out of the pavement, I call it pavement cells because these are directly constructed on the gravel layer, not a overlay. So the 506 through 806 were constructed on relatively thick base layer, which is 11-inch. Okay, and the objective of these 4 cells were to study the influence of fiber fiber dose variations. So the first one was plain concrete, then others were used with fiber reinforced concrete with the incremental doses. Okay, the cell 705 and 805 are thin concrete overlay. So I will also be talking about the structure later on when we specifically talk about their distances. And the picture here shows the fibers that were used in the construction of the cells other than 506. 506 did not have any fiber, which was a controlled section. These cells were heavily instrumented. I'm not going to read all the numbers of the sensors, but I can tell you like transverse joint opening sensors were installed. Basically, these sensors kept track of joint movement, dynamic strain gauge were there, vibrating wear strain gauge were there, and thermocouples. This is just an example of the sensor and test locations. These are actually for cell 705 and 805. Pretty much like the same kind of sensors plan were used for all the 8 cells. Thermocouples were not installed in all the cells, but otherwise the same. Again, and then these black rectangles, small rectangles, are FWD test location. You can see the test was done on the wheel path at the center, and then the different location of the sensors. So we already have a actually final report came up from this project, which is shared online, and like additional details of the sensors and test locations can be found there. All right, let's get into the question number 1. Just remind you, the question scan macro fibers help to construct ultra thin and thin concrete pavements for low volume roads. Okay, so we know 3-inch, 4-inch thick asphalt pavements, the surface layer is are common in the city state. So we saw like if we use fibers in the concrete, can we do the same thing using concrete? Little more about the structure of this two cells. Cell 139 was 3-inch and then 239 was 4-inch. All other variables were the same. Fiber was 8 pound per cubic yard, 6 feet by 6 feet slab. It was in the low volume test track. So there was like 80 plus slabs of the main road track. And total number of slabs in each cell was 180. Okay, so these are a few pictures of the construction here on the compacted gravel layer, which is the base layer. Sensors are being installed. This is a picture of the dynamic sensor. Then concrete pouring and then paving. You can see like very thin structure. And then joint opening sensors were installed later on. So you can see like this is a transfer joint. So these kind of sensors were installed at the transfer joint. So these sensors basically what it does is if you know their initial kind of reading, if you have initial reading, this reading will change with the slabs moving inward and outward. All right, now what happened in really early age, before 28 days, of course, within a week, I guess. So the construction track actually came on cell 139, and then you can see this kind of crack resulted really right after. And this crack, of course, propagated, and then they became like this kind of alligator cracking in the asphalt pavement. You can see at 35,000 equivalent single axle load, see how it looks like, and then at 63,000 esols, you can see like that. So this thin structure kind of shattered. And then, yeah, thanks to Len for doing this Drishtis map. You can understand like how much effort he had to give. So cracks all over. And then in 2018, some of the cells, basically these, slabs, some of these slabs, I think 14 slabs were replaced with 4-inch thick pavement. Now on cell 239, which was 4-inch thick, we saw far less crack. You can see longitudinal crack, and then at the end of the kind of research study, like the data collections we had on the crack, we saw like 20% slab already cracked by 2020 March, which was after 145,000 esols. So now if we design a road on a rural road, let's say, we anticipate, MnDOT's traffic category 2 is 2 million esols. So this pavement cracked, and it's still in service though, but 20% of the slab cracked in 2020 itself, just in 145,000 esols. The picture on the right shows like the location of the crack, and then again, far details are available in our research report. These are like the color-coded distress map. You can see the crack occurred almost like every year. I mean, like initially in 2018 data, you can see some black lines, and then at different years or different seasons they continued to propagate. The faulting was really less. Okay, the faulting you can see two different dates here. It's really very less within millimeter. Now, Tom has given me some data of the faulting which were collected this year in August, and then he mentioned, or based on his data, the faulting is still less in 239, and I checked the data. The maximum was 1.76 millimeter in couple of joints. So faulting was not an issue. The cracks were the issue. So what you learn, 3-inch slab was too thin on a 6-inch gravel base. So the construction of such ultra thin slab on a marginal base is not recommended, as they may fail before the anticipated design life, irrespective of fibers inclusion or not. But fiber was found to be holding the shattered concrete pieces of cell 139 for some time. Cell 239, which was 1 inch thicker, is still performing, but of course cracked. More than 20% crack was there in 2020 itself. But the performance is significantly better than 139. And also fibers are holding the cracks together. So that's kind of visible observations we have seen. And then the longitudinal cracks basically in the wheel path is the dominating distress, and it makes sense because the structure is very thin. So the distress are right under the wheel path because the load stresses in the very thin concrete is really high. Joint faulting, as we saw, it was not issue so far because we saw the cracks earlier, and then the total numbers of the ESOLs on these 139 and 239 were really far less than probably the anticipated design ESOL. So we did not see any faulting. Faulting takes some time to occur. I mean, time or the traffic load repetitions. Question number 2, can microfibers mitigate fatigue cracks and transverse joints faulting in thin concrete pavement? And if so, what is the relation with fiber doses or residual strength ratio? So in order to get the answer for these questions, we will focus on the results of cells 506 through 806. And I would remind you, these were constructed on I-94, but the design is intended for the low volume roads. The thickness, the design thickness is only 5 inch, okay, which is not definitely for a typical interstate pavement. 2 million is also MnDOT low volume road traffic level 2 categories. Okay, so from that I would say, let's say the design is 2 million. A little bit about the structure. Cell 506 didn't have any fibers, and again it is 5 inch thick. Cell 606 has fiber, 5 pound fiber per cubic yard concrete, and then we targeted 20% residual strength ratio. Even though it was planned to be constructed at 5 inch, but unfortunately, or not unfortunately, somehow the construction thickness was found as 6 inch. 706 and 806 are 5 inches, and then had more fibers, with 806 the highest, 11.7 pound of fiber, which is a lot of fiber to mix in the concrete in pavement. Traffic, again, it is interstate, generally like 1 million ESOLs per year. Okay, and this residual strength ratio reported is actually we did some test, ASTM C1609 test on the beams prepared at the site. We brought them in the lab, or we were given them in the lab, and then we tested. Again, little bit of reminding about the structure. Right under the slab, we had 11 inches of class 5Q aggregate base. The last one for cell 139, 239, it was 6 inch. Now it is 11 inch, you can see, and it makes sense. It's on interstate. Okay, and then also there were 3 inches of aggregate base there on top of clay loam subgrade. Couple of pictures. Again, this is the static strain gauge. dynamic strain gauge picture. I was there when the cell 826 was paved. These are some picture I took, or also I collected from my MinDOT colleagues. And I'm really sorry about the resolution of the picture because of the virtual presentation. I really kept the size of the file very small so that there is no delay in the presentation. This is a picture I took, a close shot of the concrete. It looks like some issues in the mixing, but overall mix was not bad. This looks like kind of good workable concrete. Well, not all. Yeah, this picture shows some sample preparation. You can see they're preparing the beam on the side. This is a little cool close picture of the concrete, how it looks like. Looks like good workable, but look at the fibers. Really, this was from again 826, which had 11.7 pound of fiber. Fibers are all over. You can see, and then they are this fiber. The nature of the fiber was you can see that did not remain very straight. It's really took the shape along with the basically followed the aggregate shape. Well, not everywhere was the workability great. This is one very popular picture. So again 806 cell, it had 11.7 pound per cubic yard fiber. So I saw something happen like that too. But anyway, eventually this is the kind of finished product. These are some pictures I took on the day of the construction of cell 806, but these pictures are not for 806. As you can understand, 806 was fresh concrete at that time. So this is from 706. Okay, 706 was having 8 pound cubic yard fiber. So, and this is 24 hours after the paving. The crack, the joint, you can see it is sawed but not deployed. I took a picture and then I walked on the edges of 506, 606, and 706. And this is a picture, and I took a lot of picture like that. So you can see a joint deployed in cell 606, which was 6 inch in thickness. All right, now let's say what distressors occurred in these 4 cells, 506 through 806. The first, this slide is showing the spalling has occurred in cell 506. Initially, we were thinking that spalling has something related to the concrete mixtures, but on some closer investigations, we found out a surprising thing. Here you can see this, the residue from the saw cut. Actually, they became hard here, and then which actually created some spalling. And then this has occurred in only cell 506, which did not have fiber. But if it had fiber, I think it would have been the same case. But these are some spalling, and I think it's just an accidental thing. We saw cracks in 506 in the first year itself, and then the total number of cracks we saw in cell 506 was 3, and all of them occurred in the same area. Now you can see this picture here on the middle, the location of the spalling and then location of the crack. So all 3 cracks actually occurred at one location. So I'm not sure, but it looks like this zone probably had some problem, or something is different probably in the base. Okay, now cell 606, 706, and 806 did not experience any cracks by summer 2020 after 2.8 million installs. Transverse joint faulting. Transverse joint faulting is, again, I remind you, like we saw this crack in 506. Now this crack, says that this slab piece here went down. If you see this kind of exaggeration or the the close shot of this location is in here. You can see the difference in the elevation. So this is the way faulting, but you can see like this faulting is not because of fine accumulation underneath the approach slab or things like that, but it's probably, I don't know, some things probably is that here maybe loss of fine. So you can see these pieces went down, and then same thing has happened to the other two adjacent slab. Now, when you looked at the faulting data for the 4 cells and we compared, definitely the 806, which had the highest amount of fiber, 11.7, it had less faulting than the cell 506, which had no fiber. You can see here this blue line versus the brown line. And then you can see like this effect of fiber dose. So here 506 did not have any fiber. Their faulting was more than the other cells with 806 low. Now all the cells actually, these are data from the different dates. As you can see, the first blue is April 2018, and the last one here is 2020. So all the cells faulting increased with the traffic. Okay, so now this was only the driving lane, and this is both lanes when we averaged. Now Tom has provided some data for August 2021 this year. Now we saw, and then we also saw here eventually like the faulting of all the cells are increasing aggressively. Maybe the fibers effects are gone or going. So you can see now 506, 606, 706, 806, they have almost the same or similar faulting values now. And this is again driving lane and the both lane averaged. All right, now, yeah, but it is outside the design life. When we looked at the load transfer efficiency with no fiber, we saw the load transfer in the very first test was really high, and then after that it really dropped. Now 606, 706, they had 5 pound and 8 pound fibers. Their behavior was not significantly different from the plain concrete, but cell 806, which had around 11.7 pound fiber, you can see with different dates, the load transfer did not decrease until about, let's say, 1.8 million ESOLs, and at 8 billion 1.8 million ESOLs, actually the load transfer dropped significantly, not almost in all the joints, but to like 1 or 2 joints probably didn't show that much of declination. This one, faulting versus ESOLs for the 4 cells, again 506, you can see it has increased. Others also increased, but after 1.8 million ESOLs, you can see like all the cells suddenly the faulting suddenly increased for these cells. We also looked at the International Roughness Index, and also we coined a factor called faulting index. Now faulting index basically take care of the faulting for all the joints, and then if you convert it into per mile, just like the unit inch per mile is same as the unit for the IRI. So these lines are basically faulting index, and these bars here are the IRI. So the IRI values for the plain concrete was high from the very beginning. You can see the blue line here. Okay, and then when you looked at the IRI value, we found out that 1.7 million ESOLs at that time, the IRI actually exceeded the value of the critical value, like 173 inches per mile, and at that time faulting was 0.1 inch. So what I would like to say here, 6 feet slabs have twice number of joints compared to the conventional joint. So if we drive on faulted joints of the small slab size compared to like 12 feet by 12 feet, which is used in conventional pavement, the IRI can be high because more number of joints even with less faulting. Okay, so the faulting values, if we, the faulting values is 0.1 inch here, but the IRI actually exceeded the threshold value. We also developed some relation between the faulting index and IRI, and we saw there is a good correlation, like more faulting, more IRI, things like that. 2021 faulting data indicates that IRI will be 173 inches per mile for. Why I said will be, because I do not have this data, but based on this correlation, I saw like all the cells should be measuring more than 173 inches. 173 is a critical IRI values for concrete pavement. With the faulting data, we also established some model to predict faulting values. And then the fitness of the model was really good. The last piece of data we had, we did not use in the model development. And then we saw like that could predict well. So see, this blue line is the model, this line is the model, and this is the data we got. Okay, so what we learned from this 506 to 806? With regards to the fatigue cracking, only cell 506 experienced 3 cracks at one location. Therefore, it is hard to quantify the contribution of fibers in mitigating fatigue cracks from this study. Regarding the faulting, fibers influence was observed in cell 506 through 806. Cell 606, 706, and 806 showed less faulting than cell 506 with no fiber. With enough loadings, though, far more. With enough loadings, far more typical design, significant faulting eventually developed in all cells. Fibers were holding the LTE higher for up to 1.8 million ESOLs. IRI for cell 506 exceeded the threshold 173 inch per mile at 1.75 million ESOLs. FRC cells did not reach to that even after 2.5 billion ESOLs. So fibers contributed to keep the IRI better. So thin pavements on relatively strong base layers seem to be safe design with respect to the fatigue cracking for low volume roads up to 2 million ESOLs. Fibers can reduce faulting and keep the riding quality until the design period, but the plain concrete pavements may not offer the same. So we saw like the 506 cell reached to the critical value of 173 even before 2 million ESOLs. Okay, question number 3. Can we construct thin concrete overlays with wider slab using macro fibers? For that, the data of cell 705 and 825 were used. Again, those cells were constructed on the interstate traffic or I-94. Now 705 had larger size slabs, 14 feet by 12 feet, 12 feet by 12 feet slabs, and then passing lane was the slab size. The width of the slab size was 6 inch or half of the other cell 705. Again, interstate traffic 1 million ESOLs per year, and the fiber used here was 5 pound. These are some pictures from during the construction time. Some sensors you can see installed, and then this overlay was constructed as an unbonded overlay, and then you can see geotextile fabric interlayer was used on top of the concrete, existing concrete, before placing the new concrete. These are some more pictures here. This is the finished product. All right, now these two cells shown significant fatigue cracks. 55% slabs cracked for 705, 55% slab cracked by October 2019. For 825, it had little less, 28% slab compared to 55% for 705 have cracked by October 2019 after 2.4 million ESOLs. Okay, so these are some more picture. By September 2022, 35% crack in 805. Again, 805 had little less, 15% less. So these graphs are showing the percent slab crack, 50% versus 35 with 806, which had small size of slab. But when we look at the crack length per unit feet length of the cell, it's kind of the same though, but number of the slabs cracked was more in the cell 05, which has larger size slab. So these are some this map, 705 and 825. You can see crack, like significant amount of the crack. Quantity wise, both have cracked. Cell 705 experienced more longitudinal cracks, 825 experienced longitudinal and other transverse and corner cracks in comparable quantities. When you looked at the faulting, faulting was very less for these cells. I mean, less than what we have seen in the 506 to 806 thin concrete pavements. These are overlay on geofabric. We saw less faulting. When you looked at the FWT test results, so initially you can see the load transfer efficiency was slow for both the cells. Okay, and then it's kind of changed randomly, or I don't know if there is any pattern, but some dates shown really high load transfer efficiency, at least on the joints where the LTE was measured. So LTE was initially low. The random changes in the LTE later in life indicates slab movement. I'm not sure, but looks like the slabs kept moving on this geofabric layer, and that's why, you know, LTE depends on the crack width. I think that probably has a role to play. Also, the lower LTE initially is probably because of the absorption of the, you know, the geofabric layer could absorb good amount of load, I would say. That's probably also resulted low load transfer efficiency in the beginning. Now we did a little small test when some slabs of the cell 825 and 705 were replaced. Here's Tom. Actually, we were doing the test under his supervision. This is a lightweight deflectometer, and then what we saw here, we did the test right just on the concrete and also on the geofabric cells. But you see, when we did the test on the geofabric cells, this grows a really high magnitude of deflections, and when we did not have the geofabric layer, the deflection is far less. So the load transfer efficiency or the high deflections under the FW load makes sense because probably the geofabric was absorbing some of the deflections, some of the load, creating high deflections. So answer to the question number 3 is cell 705 wider slab experienced 15% more cracked slab. So if we are thinking, can we construct wider slabs using fiber? Looks like no. Both cell 705 and 805 experienced minimal faulting. Cell 705 experienced more faulting, slightly more faulting than cell 825 until 2.5 million ESOLs. Dominating disease seems to be the fatigue cracking, not the faulting, unlike the other cells we have studied in this research. Cracking and faulting was more in the wide panel overlays than the narrow paneled ones. All right, the next and the last questions I will be answering here is, did we see any influence on the pavement responses? Well, we probably, we did not find out a significant influence of the fiber in the structural responses, candidly speaking, but we established some structural responses of thin concrete pavement in overlays in general. So the temperature data we collected at different season, we used to calculate the depth versus temperature relationship, basically the gradient or the temperature variations with respect to the depth. Unlike conventional pavement, you can see the temperature gradients are quite linear. Okay, so this is kind of quite linear, and the variations are different in different temperatures. So this was in July, this is in April, kind of intermediate, and this is in the middle of the winter. We saw like 60% of the time at Main Road, negative temperature gradient was there. We collected vibration aware sensor. We analyzed all the sensor data for all the slabs. We also analyzed the traffic load, induced trains, and then I'm again not really going into far details, but I can tell you that cell 506 through 806, which were constructed on 11 inches of base, has less amount of strain, okay, less amount of strain than the other cell 139. As you can expect, it had 429 microstrain, okay, so that had more. We also saw the slab curvature 506 versus 806. You can see the variation of the slab curvature was more in 506 with no fiber. Probably here the fiber did little bit of resistance to slab curling and warping. That's what we have found out. All right, so overall recommendation, this study has provided quantifiable evidence that structural fibers can positively influence the joint performance, transverse joints faulting, and IRI, etc. Therefore, it will be prudent to take the initiative to incorporate the performance benefits of structural or macro fibers into the mechanistic empirical design procedure, which currently just artificially enhances the material flexural strength to account for the fibers inclusion. So this is the key message I would like to mention and then end these presentations. So I planned on taking 40 minutes, but it is 10:43. Looks like 3 minutes was in the introduction. So Lauren, would you allow the audience to ask the question right now, or Tom will go first, finish his presentation? I'm good either way.
I think we will just move over to Tom, and then we can open it up for questions.
Okay, great. So I unshared my slides. Okay.
Are my slides showing now?
Looks like we've got Tom's up. Yep, I can see yours, Tom. And so for the audience, please feel free to use the chat box to ask any questions if you've got them ready, and we can go through them once Tom's finished.
All right, thank you for this opportunity and a good presentation from Manik leading into this. I just want to take a brief amount of time and kind of talk about how that project has been feeds into what the efforts that we've been making with fiber reinforced concrete at Minroad. So some of the lessons learned, and at the very end, I want to comment about the process that we used in this particular situation for an NRRA project. So at Minroad, we have had quite a history of examining fiber reinforced concrete in thin concrete panels, whether they're on grade or a lot of overlays. And you can see here, starting back in 1997. And at that point, the type of fibers we were putting in, at least the polypropylene, were more what we would now call a shrinkage fiber, very small diameter and very short fibers. At the same time, we had a polyolefin, which would look more like our modern day structural fibers, but at the time, nobody really understood how much to put in, so we put a massive amount in, so compared to what we're doing now. And so you can see we're kind of playing around with different variables. You know, everything's very thin, less than 6 inches. Panel sizes, we were trying different ones. We learned a lot about, you know, how they perform. And same with dosages. And very good example this time that we did that 506 to 806 with anywhere from no fiber all the way up to 12. And just to kind of again review what kind of questions are we trying to answer here is why use them? Well, we want to keep, you know, do the fibers hold the cracks together? Can we use thinner slabs? Can we use larger panels? Can the fibers serve as load transfer devices? And then another interesting one is, can we mitigate panel shifting? That's something that we've seen in several concrete overlays. A little bit, how do we expect these fibers to work? And really, the fibers are not, they work in passive activation, meaning you need the crack to form first. That's not going to prevent the crack. It becomes active once the crack comes about or within a joint system. So ideally, if this is a crack, we want it to hold the crack together. If this is a saw joint, we want to keep the aggregate interlock action as long as we can. But over time, we know that several of the joints are going to separate wide enough that aggregate interlock is not available anymore. And then we want to know, can these fibers act alone to help transfer the load across the joint? But at the same time, because it's so wide, we have to worry about slippage of the fiber out of the concrete, inelastic stretching, so we can stretch it far enough and then the fiber kind of becomes floppy within the gap, and also just breaking the fiber from the excessive forces. So I just want to talk about some of the lessons learned from all this experimentation, up into including this project I just finished. And again, these are my opinion, and they're based on a very limited set of structural fibers that we've actually tested. We've only had 2 different manufacturers, but I would suggest that the type of fibers that we're using are very commonly used amongst the pavement industry across the US. And some of the answers, again, are going to match what Manik portrayed in this most recent study, but this is more based on everything we've been learning over the time. So the question, do fibers hold cracks together? And I would say, yes, they do. And we have this example of the very thin one. Those chunks would not be staying there if there was not fibers. That was rutted about 2 or 3 inches. Those chunks would have just been pushed to the shoulder. So they do have that capability. At the same time, on many of these experiments that we've had, I've been able to go out and just pick up a chunk and pull it out by hand. So either the fiber slipped out of the matrix or the fiber does not have enough capacity. And I looked up, and an interesting fact, when you see the specifications from the manufacturer, they say this has a flexural strength of 90,000 KSI. It sounds very impressive. But that's based on the fact you'd have a 1-inch area, 1-inch area of fiber all packed together. Well, we have individual fiber strands, which if you start doing the calculation, that's ultimately a load capacity of 20 pounds per strand. So now you can understand why somebody could go over and just kind of walk over and pick up a chunk and kind of pull it out of the matrix. So they really need to be quite concentrated for them to be able to survive some of the loadings that we're putting across the joints. Now, a tight crack is a different situation, but certainly one of our things is to try to mitigate this joint faulting that we experience in overlays. And the only way we're going to do that is to have it something strong enough that can survive across a joint. Manik alluded to the fact, can we use thinner slabs? And I would agree that we're not there. The concrete itself needs to have that initial capacity because these are not pre-stressed fibers. So the concrete itself has to be able to take the initial load. We have seen, however, that if you have fibers in there, the fatigue cracking can be delayed. So it has more capacity, and that's been proven in the laboratory. And that's really where some of the criteria we get for the residual strength came from. Is the fact that once you put fibers in it, you do have more capacity. But I would argue that it's not, at least the fibers we've been using are not enough to start thinning things up substantially. And you also have to consider the thinner you go, the less fibers you're going to have crossing the joints. And that's really where we're focusing our efforts. Can we use larger panel size? And I agree with Manik, definitely not. Whether they had fibers or not, these thin, large panel overlays, I believe they curl too much. And this is what you get, is no matter how you slice and dice the panel size, if it's too large, it's going to crack. Now, what's interesting is next to these two fiber reinforced cells is a set of cells that we constructed several years ago that just had 6x6 panels, no fibers, but sitting on the same concrete overlay on a fabric, and they're actually performing quite well. So again, this tells us that the fibers are not going to save us, and they're not going to allow us to increase our panel size beyond the typical 6x6. For something this, again, you're talking about a 5-inch pavement overlay. Can fibers serve as load transfer devices? I would say not enough right now. We have seen at very high dosages, dosages so high that you start getting into placement issues, very difficult to finish the surface. Again, we did see it did delay, it did work for a while, but eventually it wears out. And same with the faulting, the faulting where we had no fibers, it was nearly immediate faulting going on. You put enough in there, it does have an effect, but again, is it practical to put that many fibers in? Can we mitigate panel shifting? I would say yes, we have seen evidence of that very much. Even, I believe, Illinois has reports showing that when they put fibers in, you do mitigate the panel shifting that goes on. And we even have it at Minroad here, you can see on the right-hand side, the section where it had no fibers. Over time, those panels, once they lose the bond, they start shifting towards the shoulder. But on the left-hand side, you can see the fibers are holding them together very well. So question is, why don't current fibers work at Minroad? As far as when I say don't work, meaning that I'd like to see more capacity out of them, especially with the joints. And some of the reasons are that the fibers that we've been using were really developed for industrial floors. And we have different loadings, we have climate to deal with. So it's kind of a tall order for a fiber that was not really designed for those criteria. Again, the current fibers do not have pre-stressing behavior. So the concrete itself has to carry the load until it cracks, and then the fibers are engaged. The fibers can really only reside within the paste. So we also have this issue that we have very optimized gradation mixes with, we want less shrinkage, we have less paste. Well, the paste is the only place that you can put a fiber. So that's something we have to also, perhaps there has to be some changes in the type of mixtures that we make. And as I shown before, the individual strands themselves are not strong enough to resist the forces. So again, perhaps the fibers that we have been using so far, we need to look for something more robust, down to even to the individual fiber itself. So question is, we've been at this for 20+ years. Do we give up and say, no, not quite yet? Because at least in our climate, from what I'm seeing, I think fibers are going to have to be necessary for these thin concrete overlays to remain competitive. Because if we develop faulting very early on, that's an extra expense over above the initial cost. So my hope is that we do find a fiber that will serve the purpose of, mitigating the development of joint faulting. And again, we've only used 2 types of fibers in Minroad experiments. There are other fibers out there that we have not had the opportunity to try, and perhaps they might work better than the ones we did. But a lot of the observations I'm seeing, even now we have MnDOT projects, and they're behaving quite similarly. So we are already going down this path, and the fact that we already have the Call for Innovation project that we're glad to have Manik involved in, and that's to develop a fiber that will serve the purpose that we're looking for. And his first task is, of course, to first identify the forces identified, figure out which forces we need to survive, Again, when I can go out and pull out a chunk, I think we need more capability than just 20 pounds per strand. Maybe the dosages that we're using are just too low. We base everything on C1609 at a 20% residual strength. Perhaps maybe that's not enough for pavement. It's good for adding fatigue capacity, but perhaps again we're looking for the aid of joint load transfer. So maybe we have to put in more. But as we know, we have to consider workability, cost, and also sustainability. If we need more paste to contain more fibers, that's kind of going the opposite direction of our focus of reducing cementitious materials in our mixes. Maybe there's other materials that, we know work, carbon fiber, Kevlar, those kind of things, but, those are very expensive at this point. Maybe at some point the price comes down enough that we could use them effectively in pavements. And interestingly enough, now, one of the initiatives we're exploring for MnROAD 2022 is actually the use of recycled materials for those fibers. So that's another added element that I think we'd like to explore. And there are some interesting things coming down the path related to that, and you'll be seeing those eventually. So that kind of wraps up at least my thoughts on where we're at with research related to fiber reinforced concrete in the thin concrete overlays and on base. And I just want to talk a little bit about this particular project, and it's one of our first endeavors, not first ones, but kind of our path forward on how we're going to be handling the new sections. And the fact that when we construct test sections at MnROAD, they far exceed the capacity that we have for the internal staff to be principal investigators. So starting with the NRRA, we decided we're going to start doling out and getting some help. And I think it's a great process, because what it does is we're responsible for getting the data collected and processed, and then we need to hand it over to somebody else to do the analysis. In a lot of respects, that keeps us on task, because before we would build a section, and we had time because we're on staff, we eventually will get to crunching the data, but when somebody's waiting for the data, we have to keep up on it, and I think that's a really great thing. We use a very open process, maybe compared to maybe something like NCHRP, where you start the project and then you wait until the end to find out what happened. We intentionally try to be very open, and this benefits both the principal investigator as well as the people on the NRRA team. You can kind of see things as they evolve, and I think that's very beneficial and kind of unique to the process we are using. We also have the benefit that we're training graduate students, and eventually we've seen some of those employees show up when we're starting to interview people. They can put on their resume, yeah, I know I worked on MnROAD data, and that's a tremendous benefit to the pavement engineering community. So where are we going from here? You're going to see there's 3 new similar research RFPs coming out soon for projects related to next year's MnROAD cells. So you're going to see this pattern again repeat, where we're going to get a lot of help crunching the numbers. And I think out of this process, I get what I call a symbiotic implementation. So, the agencies are learning as we go, and ironically enough, sometimes have enough confidence that all of a sudden they're implementing the technology before the research is done. So we have people building fiber reinforced concrete overlays already out there. We had the case of the geofabric joint drain, where we put it out there, and within a couple months, we had built a cell, but some district already adopted, said, hey, that looks like a good idea. So these opportunities come up, and again, in the case of the fiber reinforced concrete, we can treat those as satellite sites to compare how they perform versus MnROAD, and we have actually seen similar behavior, which is kind of comforting. That the fact that MnROAD, even though we're doing accelerated or very short sections, we do have a pretty good ability to predict real life performance. With that, hopefully that kind of helped give you some perspective on where we're at with research related to fiber reinforced concrete, and also the process we're using with the NRRA. Thank you, and we'll take questions now.
Thank you so much. I am going to I'm going to allow the mics for attendees, because it was previously not on. Looks like we do have questions loading here. Question is, how does this affect future recycling of concrete?
Tom, you want me to answer this question?
No, go ahead. I mean, I guess my answer would be, I don't think it should affect mud. It's certainly at the concentration of fibers that we're putting in our typical project, which is maybe 4 to 5 pounds. I don't know that that's going to be an issue. But again, we have very little experience in this. You know, these are newer projects.
I agree with Tom. And then if we use the recycled, let's say, fiber reinforced concrete in another, let's say, concrete for a lower lift or a little weaker concrete, I don't think the fibers will interfere in the strength of the concrete produced using recycled fiber concrete.
Okay, looks like Bernard has his hand raised.
Yes, can you hear me?
Yes.
Yes.
Okay. Yeah, very great presentations from both of you. Very, very informative. I just have a question that actually is somewhat also related to a method that we developed here at MnDOT, the method of evaluating the interfacial strength of pavement materials or materials within the pavement structure. And that's the aggregate avoidance index. You know, I'm just wondering, because this is based on the interfacial transition zone, which is technically, supposedly the weak zone in concrete. That's the very thin space between the aggregate and the paste. That very thin area, you might have a little more moisture there, and then it becomes weaker because of the high moisture content. But aggregates that have desorption and adsorption properties do take care of that region significantly. And then you have better performance when you have things like internal curing, or even to some extent, some recycled aggregate that have absorption, but they don't have very good desorption properties. So I've always wondered, fibers, what will fibers do at that interfacial transition zone? Do you think there is an enhancement there, or is the enhancement just in the matrix? What's your take on that?
Thanks, Bernard, for really very good question here. So the project that we have done, I can tell you we did not have a kind of component there to study the influence of fiber on the ITZ, but based on a lot of literatures and then our results too, it seems the tensile strength of the fiber reinforced concrete doesn't decrease. Okay, if it is synthetic fiber, let's say structural synthetic fiber. Again, I'm talking only on the strength of the materials. Let's say tensile strength does not decrease. People found out increase in the tensile strength. Modulus of rupture, if we use synthetic fiber, it does not increase too much, but it increases a little bit or it doesn't decrease. So now, if the fibers negatively influence in the ITZ, with respect to the strength, I would say no. Okay, but again, this answer is only my experience on the literature. I have not done any specific research to find out if fibers weaken the ITZ. Looks like no. So that's my answer to your question, Bernard.
Okay. Thank you.
Thank you. We are a little bit over time now, so I understand it if folks need to head out. I wanted to give just a couple of quick announcements. We will not be having Research Pays Off next month due to the MnROAD NCAT fall sponsor meeting is also happening that week. And so we're going to just cancel that for next month, and then we'll rejoin back in November for the Flexible Team project update. This has been recorded, and I will be getting it up to YouTube within about a week or so. So you can watch for that if you need to come back and reference any of the information. Any other questions before we sign off? I'm not seeing any. So with that, I would like to thank Manik and Tom very much for sharing that information, and thank you for joining us today, and we will see you in November.
Thank you very much, Lauren, and all the participants who attended today. Yeah, I really appreciate. Please feel free to email me if you have any questions. So, and then my email address is available on the presentations slide too. So you can reach out to me.